Hello everyone, welcome to this lecture in the Neural Networks from Scratch series. Today we will be talking about a very important subject and that is related to optimization. So let me quickly summarize what all we have covered up till now. If you look at this schematic of a neural network, up till now we have implemented a method to do an entire forward pass and then to calculate the loss between our predicted output and the true value. Here is how the forward pass actually looks like. We have an input which currently has two features x1 and x2. It goes through a first hidden layer which has 3 units. Then it goes through the second hidden layer which is also our output layer in this case which has 3 units. And then those three outputs will then tell us something about the loss. We looked at different activation functions. In the first hidden layer, we have used the ReLU activation function, and in the output layer, we have used the softmax activation function since this is a classification problem. Up till now, the problem which we have looked at is something like this. We have data which is called as a spiral data set, and it looks like this, what I'm showing on the screen right now. So each data point has two attributes x1 and x2 and it belongs to one of the three classes red, green or blue. And the goal of the neural network is ultimately to predict from these output neurons that whether it belongs to the red, the green or the blue. We implemented different classes in Python. The first class which we implemented is the dense layer class. Then we implemented a class for the ReLU activation function which you can see over here, class activation ReLU. And then we implemented a class for the softmax activation function. Initially, we did a forward pass without the loss, where we chained these different classes together. First, we created a layer using the layer dense. Then we chained an activation class to it. Then we created the second layer, and then we chained the softmax. Exactly like what I've shown in the schematic here. And in the previous lecture, we looked at loss. So we understood what is the cross entropy loss. We created a class for the cross entropy loss, and then we integrated that also along with the forward pass. So the full code up to this point is given here. We create the first layer, then add a ReLU activation, create the second layer, add a softmax, and then finally add the categorical cross entropy loss. This is where we have reached up till this point. We also looked at accuracy and loss as metrics for predicting whether our neural network is doing a good job or not. Up till now, we have not seen anything about tuning the neural network weights and biases. We have not seen anything about how to find the optimal weights and biases which reduce the loss. All we have seen is if the weights and biases are initialized to some random values, how can we get the loss in the first place? So the first layer has weights W1 and bias B1, and the final layer, which is the output layer, has weights W2 and bias B2. Uh, Currently, the values in each of these matrices are initialized randomly. So, for example, if you look at the W1 matrix, it will be like something like this. So, the first neuron will have two weights, the second neuron will have two weights, and the third neuron will have two weights. So, this is the W1 matrix, and the bias will look like this. So each neuron will have one bias term associated with it. So if you look at W1 and B1 in terms of just numerical values, there are six numerical values in the matrix W1, and there are three numerical values in the matrix B2. So there are nine values here. Similarly, if you look at W2, so if I write down W2, the first neuron weights will be 3, second neuron weights will be 3, and third neuron weights will be 3. So this is a 3 by 3 matrix. And if I write B2, which are the biases associated with these final neurons, each will have one bias. So that will be a 3 by 1 matrix. So if you look at W2, the number of numerical values are 9. And if you look at B2, the number of numerical values are 3. So if we add the total number of numerical values from the first weight and bias, it's 9, from the second it's 12. So total there are 21 values which are not yet optimized. Those have been initialized randomly. What if there is a minimum, or what if there are some best values for which the loss is very low? The question is how to find these values. So just to give you a visual understanding, let's say if the loss function looks something like this, and we are currently here with the current values of weights and bias. The question is how to find the weights and bias values which get us to this minima point. And the whole of neural network literature, henceforth, is dedicated to gradient descent methods and backpropagation, which exactly help in solving this problem. But now you can imagine that you are a student or a researcher who is living in a century or living in an age where backpropagation and gradient descent have not yet been discovered. And someone asks you that I have weights and biases which are initialized to some random values. Can you help me to find the best values of these 21 parameters, the weights and biases, so that the loss is minimized? Let us think of some strategies which we can implement to adjust the weights and biases to decrease the loss. So, if we have no knowledge of optimization procedures, gradient descent, or backpropagation, the simplest strategy which you can think about is this, right? Okay, let me randomly select weights and biases. So I'll pick weights and biases completely randomly. I'll calculate the loss, and I'll do this for 100 times, 1000 times, 10,000 times. And then the hope is that I will eventually hit the weights and biases which minimize the loss. So in this analogy which we have described, the first strategy, which is the first thing which comes to your mind, is okay, this weight and bias did not work, let me try this, let me try this, let me try this, let me try this. So let me just keep on trying 10,000 times, and hopefully something will work. It's like trying to put an arrow on the dartboard, hoping that something will stick. So that's the first strategy, and it's not a bad strategy. Let's just see whether it works or not. So you come up with this strategy, and you tell to that person that I can help you find the weights and bias which minimize the loss, and I have this strategy for you. Let us see whether this works in practice or not. So I am now going to the Jupyter notebook where I am going to implement this strategy. And for this, we are going to take a simpler data set. In the spiral data set which we looked before, the data itself was a bit complicated. To illustrate this, I am going to take a data set which looks something like this. This is also called as a vertical data set. So again, there are three categories: red, green, and blue. And these are the points. So this is my input data. Every input again will have two features, x1 and x2. Okay, this is the input data, and the goal is that you have a neural network like this which takes in the input data. The x1 and x2 are the two features. You have the first layer which has three neurons, you have the second layer, three neurons, and you have the cross entropy loss. The goal is, using this strategy, try to find the weights and bias which minimize the loss. So let's try to understand what to do. Initially, let's define an instance of the layer dense class. This will create the first layer. Remember, the first argument of this class is the number of inputs in that layer. Second argument is number of neurons. So in the first hidden layer, we have two inputs and three neurons. So it's 2 comma 3 here. Then this is the second layer, which has three inputs, which are the outputs from the first layer, and it has three neurons. The first and the final activation function is the softmax, and the first activation function is ReLU. So we also create instances of those classes. And finally, we create an instance of the loss, which is the categorical cross entropy loss, which is applied at the final output. Okay, great. So I am going to first initialize the weights and biases fully randomly. So here the dense one weights means the weights of the first layer. Best dense one biases are the biases of the first layer. Best dense two weights are the weights of the second layer. And best dense two biases will be the biases of the second layer. Um, and this will eventually contain the value of the best weights and biases for me. Currently, I have just initialized them randomly. So dense one dot weights will give me weights which are initialized when you instantiate this layer dense class. So those are weights which are sampled from a Gaussian distribution. Biases are initialized as 0. Dense 2 dot weights will give me the weights as initialized by the layer dense class. Those are again Gaussian, and dense 2 dot biases will give me 0 values for the biases. Now here you can see that I am going to do 100,000 iterations, which means I am going to try to hit that arrow on the dartboard 100,000 times, hoping that something will stick. And as you can see, at every iteration, I am going to initialize the weights and biases randomly. So remember, the first weights has the dimensions of 2 rows and 3 columns, as we have seen over here, 2 by 3, and the second weights has dimensions 3 by 3. So when you initialize the first set of weights, it's a Gaussian distribution 2 by 3, and you multiply it by 0.05. So it will create a matrix exactly with the same dimensions as this, and it will initialize it randomly from a Gaussian distribution. This is similar for the biases, uh, and for the second layer weights and for the second layer biases. Remember that the argument which you give to np.random.randn function, it will create an output of exactly the same size as this argument. So for example, np.random.randn 1 comma 3, this will create a matrix whose dimensions are 1 row and 3 columns. uh, so basically it will be like, it will create the bias terms. So this can also be represented as 1 row 3 columns. Okay, so at each new iteration, we are initializing the weights and the bias term randomly. And then we are doing a forward pass through the first layer. We are applying the first layer activation, which is ReLU. The outputs of the first layer, which is activation.output, will go to the second layer. And then we finally do the softmax output, which is the final layer output. And that is then passed to the loss function. So then we find the loss between the prediction and the true value. And then we are also going to print the accuracy here. One thing which we do here is that if our current loss is less than the loss of the previous iteration, we change this best dense weights to the current values because the loss is lower in the current iteration. So ultimately, the best dense one weights, best dense one biases, best dense two weights, and best dense two biases will contain the optimized weights and biases of every layer. Now let's run this function, and I'm printing it only when the loss in the current iteration is lower than the loss in the previous iteration. So only if the loss is lower than the previous loss, or the lowest loss up till that point, I am going to print the current weights and the current accuracy and the current loss. So let me print this part. So I'm running this right now, and it will run for some time because I have 100,000 iterations here. So currently you will see that although number of iterations have proceeded 11,000, it has printed only around 10 times, because it only prints when if you are at an iteration, the current loss is less than the lowest loss found up till that particular point. So here we can see that it has printed till iteration number 10,848. So if you look at the loss up till this point, it's not decreasing at all. In fact, the loss has started out with 1.099, 1.099, and currently it has reached 1.095. Let me wait for some time here until the uh, iterations are finished, until the 100,000 iterations are finished, and then we will check how the loss varies for all of these iterations. Okay, so here you can see that we have printed the loss at iteration 93,926. and the lowest loss up till this point is 1.095. In fact, all the iterations have finished. It took about 1 minute. So let us track the loss. The loss which is printed here is the lowest loss which we have obtained in 100,000 iterations, and it is not very less from the first loss which we started with. So this strategy turns out to be not very good at all, and in fact the accuracy is 0.33, which is like a coin toss. Because if you look at the final output, uh, the if the accuracy is 0.33, it means that with 33% confidence we are, if the input is red, if the input is red category like here, with 33% confidence we are saying it's red, which is essentially like not confident at all. So the loss did not decrease too much, the accuracy also did not increase too much. This is the first indication that this strategy is not good at all and it does not work. The reason it does not work is that when we use neural networks, we are typically in a high dimensional space. So the functions which we have don't look as simple as the one which we have plotted here. We have so many parameters. Here we have 21 parameters. And there is a huge number of variations of weights and biases, and we cannot try all of them, right? We did 100,000 iterations, but even then, it's very difficult to find the best weights and biases. So this strategy does not work at all. So we think of something clever. We think that, let's say in one particular iteration, the loss actually decreased. So let's say that earlier what we were doing is that, let's say if this was the loss function curve, so in one iteration if we were here, and in the second iteration if we are here, this is actually good for us because the loss is decreased. But in the previous strategy, we did not take this information into account. For the next iteration, we went randomly to another place. So in this strategy, what we do is that we say that if in the current iteration the loss is less than the previous iteration, the next weight and biases which you try should be closer to the weights and biases which you tried in the current iteration, because you generally seem to be headed in a good direction. So if the weights and biases here were W1 and B1, the next weights and biases should be close to W1 and B1, because these weights and biases reduced your loss and you seem to be moving in the right descent direction. So this is exactly what our second strategy is. The first strategy was randomly select weights and biases. Our second strategy is going to be randomly adjust weights and biases. The difference here is that if we notice that the loss decreases for some weights or biases, the next value of weights and biases will be chosen to be closer to the current value of weights and biases. And if the loss increases, so let's say if we turn out to be going in the other direction here, then you simply don't update the weights and biases. You keep it what it was in the previous iteration. This is also different than the previous strategy where even if the loss increased, we randomly chose some other value in the next iteration. We did not stick with the previous value. So there is a lot of good things which we are doing in the second strategy. We are encoding some previous information of the previous iteration. So now let us see how well this strategy works. I am again going to the code right now. For the first strategy where we randomly selected weights and biases, it did not work. So now what we are going to do is we are going to implement the second strategy in which we are going to randomly adjust weights and biases. So the layers and the activations will be initialized in a similar manner. First layer instance, the activation ReLU instance, second layer instance, and activation softmax instance. They are initialized. But the way we do the rest of the code is a bit different. So very similar to the previous code, we define the best dense weights and biases, which will ultimately contain the optimum value of the weights and bias. When we start the iteration, when we start the iterations, you will see that instead of just in the previous code, this was just dense dot weights equal to, right? But now we are saying plus equal to. Essentially, if you look at this part of the code here, if the loss of the current iteration is lower than the lowest loss, then we update the best dense weights and best dense biases. And what are the updated values? The updated values are you just add something small to the previous values. So these four statements which are over here, they will be invoked if the current loss is lower than the previous loss. And this plus equal to here makes all the difference. The plus equal to means add this small value to what your current weight and bias matrix is. So this indicates update weights with small random values. And this will be done only if the current loss is lower than the lowest loss up till that point. So the updation will be done only if we are kind of moving below this parabola. Else, nothing changes actually. Else, you revert back to the original weights and biases. That is the simple code which has been written here. Everything else is very similar to the previous code. So let me run this piece of the code right now. So here you can see that I am running for 10,000 iterations, and we are going to see the changes in the loss. So first of all, you can see that the loss is now decreasing, right? The loss started with 1.099, and with every subsequent iteration, so at the iteration number 100 it was 0.96. At the iteration number 1000, the loss was 0.17. In the earlier iterations, the loss never went below 1.09. So we are actually doing very well here. In fact, if you go below and if you see till 10,000 iteration, so now this code has run, and if you see till the last iteration, we have got the lowest loss as 0.16. So the loss has reduced by almost 10 times which we started with, and our accuracy is 94%. This is much higher than the accuracy of 33% which we had gotten in the previous strategy. So actually it turns out that this particular strategy does work for the example which we considered here, the vertical data set. And if you do this strategy for 100,000 data points, currently I'm showing for 10,000, right? If you do it for 100,000 iterations, sorry, or if you do it for 1 million iterations, you will get an accuracy of even higher, like 0.95 or 0.96. So it turns out that strategy 2 does work for this vertical data set. So this is amazing. Without needing back propagation or gradient descent, you have converged on this strategy. But now you would be thinking, then why do we even need to study back propagation? I can just implement this strategy to optimize every neural network out there. But it turns out that this strategy is not robust to different data sets. So we used a simple data set here, right? Now let's try with a more complex data set, which is the spiral data set. So the only change which we'll do here is that here the x and y were taken from the vertical data. What I'm going to do now is that I'm going to take the x and y from the spiral data set, and I'm going to run this same code again, and now let's see the loss. So I'm going to run this same code again, and now you can see that the loss is not decreasing too much. Initially the loss was 1.1. Let us see, after 3000 iterations the loss is 1.06. After 5000 iterations the loss is 1.06. And let's see if this code is still running, but it will finish in some time. Now it has fully run, and you can see the loss. When I reach the end, the loss is 1.04. So the loss started out with 1.1 and it has reached only 1.04. And the accuracy is also zero point 0.4, which is very bad, and even the loss did not decrease too much. So it turns out that this method is not robust at all. In fact, it works for some data set, but it does not work for complicated data sets. So we cannot work with this method also. So both of the strategies which we thought about, the first strategy did not even work for the vertical data set. The second strategy which we thought about, it works better, but it fails for complex data. That is the reason we need to encode some more information about whether we are moving in the correct direction or not, and how we should update the weights and biases. The reason the second strategy was working in a better manner is that we were kind of updating the weights and biases whether we are moving in a based on whether we are moving in a correct direction or not. That is good. But the way we are updating them is not good. We are updating them randomly, right? We should update them in a specific manner. In fact, the exact specific manner to update the weights and biases is taking the slope of the function. So let's say I'm currently at this point, right? Uh, the best way to decrease the loss sharply is to go along the negative gradient of the slope. So how much amount the weights and biases needs to be updated, it actually depends on the gradient of the loss function. And that is why calculus comes into the picture. If we did not need to find gradients, then people would not say that you need to study calculus to understand neural networks. But the important thing is that derivatives actually give us an indication of which direction are we moving. So it turns out that the negative of the gradient at a particular point is the direction of the steepest descent. And if we move in that direction, we are optimizing the loss at a much faster manner. That's why we need to find gradients. So the second strategy is good, but the way we move when the loss is decreasing, it should be determined by the slope or the gradient at that particular point. And that's why we need to study optimization in a better manner. We need better ways to do optimization. So in the next lecture, we'll be covering the basics of derivatives, gradient, partial derivatives, and chain rule. Once these four things are mastered, then we are on track to learn about backpropagation, which is how to update the weights and biases so that the loss keeps on decreasing. But before that, as I said, we need to learn four things: derivatives, partial derivatives, gradient, and the chain rule. And these four things will be covered in a separate lecture. So, thank you so much, everyone. I look forward to seeing you in the next lecture.